Okay, folks, so I'm officially hitting the record button. We are game on. Congratulations on being the now 16 people that officially have power in New England. So today's class is going to be lesson 26. And lesson 26 is life after Solidworks. Yes, there is life after Solidworks, believe it or not, folks. So if you want to go over and join me and watch the slides, that's fine. If you don't, that's fine too. You can just watch along. So life after SolidWorks, guys. Let's talk about how we're going to convert that cool model you made into something that's real, that can actually be manufactured. Because believe it or not, nobody pays you for blueprints, nobody pays you for solid models. They pay you for stuff that they can make and sell. The plans for a Corvette fender are great, but until it's on the car and can be sold, it means nothing. Okay, so let's go over some general tools, general stuff of how we make parts in the world. And the first one I'm going to talk to you about is milling. Okay, so imagine you've got this cutter and it's a lot like a drill bit. It spins around to remove metal and it can go down into the metal, but unlike a drill bit, this thing can go sideways. So here are a couple different examples. We've got a roughing mill. So when I just want to go fast and take off a lot of metal, I would use something like this. The little serrations reduce the horsepower required, and you will just rip material off with this. And then chances are what you're going to do is you're going to come back with something like this 6 flute. You're going to make a nice slow pass. You're going to take off just a little bit of metal and get down to your final dimensions. That is a very common way to do things. It's called roughing and then finish milling. Okay. So as long as you got the horsepower to drive these fine mills, these are great. Really nice surface finishes. Okay. And you can make stuff that looks kind of like this. So I can plunge down with that cutting tool and I can go roundy, 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 and I can cut out pockets, or I can come off the side and I can make step geometry like this. Okay. So that's what you do with a common flat end mill. Probably the next most common mill for taking off metal is this thing called a ball mill. So remember when we were doing fillets, uh, we had those nice little rounded edges. Well, this is the tool that actually makes it. So with a ball mill, we can do stuff like this. We can create rounded bottom pockets, and these are nice. You know, maybe you've got a highly stressed part, something like aircraft landing gear, something like that, and you want to round the edges so you don't create a stress concentration. And you will learn all about that in your FEA class. Uh, but that ball mill is how you're going to actually create this. And if you want to create a fillet on the edge, same thing. You're going to take that ball mill and you're going to come right in. Now, remember, for example, on this corner right here, I still have to have enough room for the rest of the ball mill right in here. So as you're sitting there dreaming up these amazing parts, I want you to think about that tool and think about, okay, do I have enough room to get it in there? You're probably not familiar with the heads, but just, you know, start thinking about what is the tool that's going to make this? Can I fit it in? Stuff like that. That will go a long, long way toward helping you guys get through your first design reviews out in the real world. All right, so what else have we got? Okay, there's another way that we can use a ball mill. Let's say that we want to create these cool, slopey, organic features that are done on things like coffee makers and, you know, consumer products, stuff like that. What we can do is we can take that same ball mill and we can run it right across the surface, cutting material away. Then we'll go back over it and we keep going back and forth along the part until we can mill this actual smooth, swoopy kind of shape. Okay. Takes a lot of time, takes a lot of computational horsepower to make these tool paths. But if you're doing it for something like a mold, where you're just going to shoot plastic in and the part pops out after 2 seconds, this might be an absolutely fine way to do things. Okay, so just make sure that your process matches the volume of the parts you're going to make. And Professor Code is going to teach you about all that kind of stuff in great detail in MEE 330. That's his big specialty. Okay, but the other thing I want you to remember, see how this has a certain radius? Okay, if you're going to get down inside the contour of this swoopy shape, the radius of the ball mill has got to be less than the radius of the feature you're trying to create. So you can imagine if I were to try to cut this out with something the size of a bowling ball, yeah, not going to work. The bowling ball is just not going to fit down inside this trough, which is why you've got to use something small. Small cutters, finer detail. However, smaller cutters mean you can go down less distance because of bending, and you have to run them much, much slower. So there's a trade-off in there. And again, if you're doing something like this, maybe you want to come in with a big tool first and just lop off a whole bunch of metal, get you close, a kind of close shape, then come back in with your fine tool and do it a cleanup. So that might be a good way to do, a mold or a complex contour like an airfoil, something like that. Okay, you can also get tapered cutters. So if I were to plunge this thing into a piece of metal, I'm going to get angled faces. And again, this is kind of a mold making tool. I included this in the course because almost every job I've had, as an R&D engineer, I always ended up making plastic injection molded something, whether it's medical consumables, um, aircraft lost wax molds, something. You're going to run into molding a lot if your career is anything like mine was. Okay. So that's how you make an angled face. If you want to do an external fillet, say we do something like this. We want to do a nice edge break so that you don't whack your knuckles on it and cut your knuckles up. Well, we're going to use something called a corner rounder. And this is what it looks like. And what I want you to notice is, look how big and bulky that thing is. So if I make a rounded edge and I had some other geometry in close here, there's no way I can make that. I have to be able to get this tool in and still clear all of the other stuff around it. So just start thinking about that as you draw your parts. And of course, the venerable drill bit. Okay. Typically, and there are drill bits for all kinds of stuff out there. There are drill bits for drilling glass, concrete, wood, metal, hard metal, soft metal. I mean, drill bits could be just almost an entire course. But to cover it in just a slide or two, typically you're going to see a 118-degree drill point on a common American drill. Slightly less common, but still out there, you'll see a point of 135 degrees. So for those of you that are still insisting on, you know, cut extruding circles to make holes, okay, if you send that off to a manufacturing guy, they're going to pull out this tool to make the hole. And it's going to have a coned point at the bottom of the hole. And then they're going to come back to you and they're going to say, do you really need me to mill that hole? Or can I use a common drill bit? This is very, very fast. Whereas milling a flat bottomed hole, it can be done, but it's just a lot more time, therefore more money. So if you need to make a blind hole, have the cone at the bottom, make sure it's there. Otherwise, somebody's going to come talk to you. Okay, so as always, use the darn hole wizard, folks. And also, when you're designing stuff, anytime that you're making a hole and you can drill all the way through and maybe put a nut and bolt on it, okay, that's always the better way to go. Anytime that you have what they call a blind hole that doesn't punch out the other end, especially if you're going to thread it. Okay, I don't know how many times I've had to thread a blind hole. I'll twist the cutter down in, it hits the bottom and snaps off. And then there's copious swearing and everybody's mad and you got to throw the part away and start over again. So if you can drill through without affecting anything, by all means do it. That's a very common newbie kind of mistake. Okay, so let's keep going with our cool part. So let's say that, you're doing that aircraft filler door for the hydraulic system on a 737. And you don't want to have bolt heads out in the airstream creating drag. You might do this countersunk screw. And then you got to make this cone-shaped countersunk hole. Well, what does that countersink look like? Looks like this. So your CNC machine will come over, it'll pick up one of these, it'll sink it to the correct depth. I want you to remember, if you're using American fasteners, this angle at the point is going to be 82 degrees, just like the one shown here. And if you're going to use metric fasteners, this is typically 100 degrees between these two cutting edges. Okay, so do not mess that up. And you can also get drills with integral countersinks so that you can go down to a certain depth, cut the countersink, and do the whole thing in one operation. So if you're General Motors and you're worried about cutting 2 seconds off the cycle time because that saves you $50,000, there are drills with countersinks. Somebody's giving really bad feedback. All right. Maybe there's just water in my internet connection this morning. Okay. So those are the most common basic rotary tools where we spin the tool as a method to cleave metal and create a part. So now let me show you how we actually do that. How do you create those fancy tool paths? And let's see. Okay. Oh, don't tell me this is going to give me sound problems. Okay. It's not mute. Same as system, same as system.
I think when you share your screen, there should be an option to share your audio as well.
Thanks, Sam. Advanced sharing. So that's multiple, so you guys can see it. Ah. So now let's try this. Oh, come on. Stop doing that. All right, let's see if we have sound now. Huh. Still muting. All right, we have ways around this. Okay.
If the video is embedded in the slideshow, we can just all go watch it.
You can. So let me just point out a couple of important features. So in this important part, what I want you to get out of this video, see how I've created these square corners in the mouth of the happy face? Okay, I'm going to take that rotary tool and I'm going to program this SolidWorks part to try and actually create it in metal, as you're seeing here. So what happens is you come down, you face it off, just like this. So now I know that I've got a flat piece of metal. I cut the eyes out. Well, everything's going great. My tool's spinning around. I go around the perimeter. But then when I make the mouth, even though I've got the square corners, because I'm using a rotary tool, I ended up with round corners on the mouth. Okay, this is a classic new engineer kind of mistake, guys. Okay, I can't tell you how many times I've kicked back either grad student designs or capstone senior designs because they tried to use a rotary tool and go into a square corner. Okay, huge, huge mistake. So Always watch out for that. Excuse me. That was the point. And if you want to actually see the full process for CNC programming, over here on the videos. Hi students. In this video we're going to go over how to create G-code for running a CNC machine from a Solidworks solid model. And we're going to use Fusion 360 to accomplish this. The first thing I want you to notice is that I have this part and it's got rotary features, it's cylindrical, but it also has this square shape on the top. Okay, this would be kind of difficult to do on a hand machine. The other thing I want you to notice is the orientation in the coordinate system. So X and Y are representative of where the milling table would be, and Z is in the direction of our tool. So if you can imagine, we're going to have some cutter that comes down and clears out that pocket. You want that cutter to be parallel to the Z-axis. If that's not the way you drew your, you create an assembly, bring your part in and then export that part as a Step 203 file. Because I have mine properly aligned, we can go directly to the Step 203 exporting step. Step 203 is a file interchange format that was developed by NASA so that different CAD systems could talk to each other. To do it in SolidWorks, we're simply going to say File, Save As, and instead of Part, we're going to choose Step 203, right up here, and I'm going to call it Test Part 2 and put it on my desktop. And I'll hit Save. So now here's my Test Part 2 right here. Okay, let's go over to Fusion 360. This is an Autodesk product. And the first thing we have to do is upload it into Fusion. And guys, Fusion is free to students. So if you want this, you can just download it off the desktop. And let's see, we'll go down to test part 2 dot step, and we'll say open and upload. And for most of our parts, this shouldn't take very long. They're relatively small files. Okay, so our status is complete. We can hit close. And over here, we should see our test part 2. And here it is. I'm going to double click on that. And here's my test part. We'll get rid of this file dialog box so I can maximize the screen. And over here, we have our design functions box. I'm going to come down to manufacture, and this is where we're going to be allowed to create our G-code. I'm going to change the units to inches just because I drew it as an inch part. Doesn't matter, you can mill in metric just as well as English, really doesn't matter. Okay, so under setup, and here's one of my classic bobbles. It's being a little fidgety. Okay, let's go right on to our milling functions. So we have 2D milling functions and we have 3D milling functions. Most of what we're going to do is going to be 2D. 3D is when you get into fancy stuff like carving or faces that are constantly changing. So this would be your
Okay,
contour
so we're going to
milling.
start off with a facing operation. And notice that Autodesk brings up a little representative picture of what's actually going to go on. Facing is something you're typically going to do in the beginning. It's going to flatten your material and it's going to give you a zero reference face to machine the rest of your part from. So I'm going to click face and my dialog comes up. The first thing I need to do is choose a tool. So what tool am I going to use? What's my cutter? I'll choose all. I'll choose the operation. So we're going to do facing and I'll say OK. These are the tools that are commonly used for facing. I want to use a flat 1/4 inch end mill. So I'll say OK. And the program automatically gives you the tools that are appropriate for that operation. I'm going to pick a 1/4 inch flat 2-flute end mill and I'll say OK. And notice you can see the 1/4 inch end mill and you can see the holder for the end mill up here, which is kind of jazzy. Okay, we're going to set our spindle speed. We're going to imagine we're doing this in the Crosby machine shop on the Tormach. 4,500 RPM. If I don't select anything else, it's going to face off the entire top of the part. We can modify that if we want. So I'm right-clicking, I'll hit Edit. I'll choose the geometry. And notice it faced off just slightly above the part. I think I'd rather have it face directly on this surface right here, this top surface. So I'll choose that top surface. We're going to set our heights. And this is where we get into things like clearing any hold down fixtures, stuff like that. So our bottom height, I like to work from the bottom of this menu up. Our bottom height is going to be our model top with no offset. So that's the bottom of where the cut is going to be made. Our top height is going to be the stock top. Our feed height, this is when you just want to move across the top of the part. So we'll move across the top and we'll clear by 0.2 inches. That sounds good. The retract height, if I need to go over any hold down clamps. And the retract height, again, this is if you got to go over something really tall. Okay. I'll do that. That all looks good. I'll go on to the next one. The number of passes. Okay. So if my part were really deep down inside the piece of stock that I was going to use, I might want to go with multiple depths, and I could say only take off, say, a 1/16 of an inch at a pass. I could do that. See, and that all looks good. Stock to leave, this might be important. Maybe you're doing a roughing operation. Maybe you want to come in with some big solid tool, take off a lot of material, and then come back in with a finish tool. You could leave stock on intentionally and then just take a fine finish cut. So that might be important to you. And nothing here that we really need, so we'll say OK. Fusion thinks about it, and here is a preview of the path that it just created. Okay, not bad. Let's add another feature. So the general process is we keep adding features, or excuse me, machining operations to create all of the features that will then yield our final desired shape. I think the next one should be a 2D pocket. And let's clean off this shelf. Again, I'm just going to go right across these tabs in the top. So we're going to use the same 1/4 inch end mill, 4500 RPM. The geometry, I clicked on the face, so it's going to clean off this face for me. I'll set my heights. Now notice my heights are not correct. This is the bottom of the cut right here, and it's not on the face that I want. So I'm going to again go from the bottom of the dialog to the top. Bottom height, I'm going to say right there. Top height, I'm going to select the height that I want. I'll do a selection on that edge. That'll be the top of my cut. This one I'll set at the top of the model and offset it by 0.2 inches up, so that's okay. The clearance height, we'll set this at the model top plus 0.4 inches. No red error messages, we're good to go. Passes, again, it's assuming stock to leave, so it's leaving some material for cleanup. I don't want that. What I do want, however, is to do multiple depths so I don't take off too much material at a pass. And I'm going to say 0.07 inches to take off on every pass. And I'll say OK. And there's a preview of the operation that's going to occur. So we've faced off the material. Now we've created this step. I've just clicked in the background. So now let's do the center bore. We're assuming a 1/4 inch end mill. This is a 1/2 inch hole. What we can do is we can orbit that tool around, just spin it right down in, and create any size hole we want that is greater than a 1/4 inch. Let's do that. We'll say 2D, bore, so that means go drill a hole with the end mill. First one looks good, 1/4 inch end mill, 4500 RPM. Circular face selection, so I got to click on the face, and you can see the preview of what's going to happen. That looks pretty good. Now we got to set our heights again. Going to work from the bottom of the dialog up. This one I'm going to say model bottom, so that I drill all the way to the bottom.
I actually like to
Top
drill a
height
little bit
will
below.
be my model top.
That assures I pierce through.
And then the retract height and the clearance height, those all look good. No stock to leave. And multiple passes. Step over of a 1/4 inch. This one I'm going to change the pitch to 0.07 inches. Didn't like that. So we'll go back and edit it.
The reason it didn't like it, guys, was because the tool is a 1/4 inch, the bore is 1/2 inch. You only need one spiral to make the hole. I figured that out after the fact.
Okay, so it wasn't liking the multiple passes. There's our pathway. Let's try it one more time.
I'm a glutton for punishment.
That's a better looking spiral. So it's just going down in a little bit faster. Sorry about those errors. Okay, so that gives us this step, faces off the top, does the bore. Now we need to put in these kidney bean shaped pockets. So we're going to do a 2D pocket. And you can do multiple features at once in one milling operation. So again, we'll go right across. 1/4 inch tool, that's good. Geometry, I'm going to choose the bottom edges. There we go. Again, I will set the heights. So the bottom height will go from the model bottom. The top height, I'm actually going to do a selected contour on that. Let's get this up a little higher. So we'll do a selection. We'll select the top of that edge. The feed height, the retract height, those all look good. The passes, we're not going to leave any stock. We will do multiple depths. So let's make this 0.07 inches. And I'm going to click OK. It thinks about it, and there we go. We've generated our toolpath. And the last thing we need to do is cut this part out of the material. So that is typically done with a 2D contour. This is what I often use as my last step for cutting the material out. So 1/4 inch end mill, 4,500 RPM. I need to select my contour. So I'm going to choose the bottom edge. And let's see. My heights, again, I'm going to start at the bottom. I'm going to go to model bottom so that it cuts all the way through to the bottom of my part. The top height, I'm going to say I want it to cut from the model top. And that all looks good. I do not want it to cut the whole thing in one pass. So we're going to go with multiple depths. And we're going to go with 0.07 inches. And there's a representation of what's going to happen. It's just going to keep spiraling down in until it cuts the material free. Okay, so that looks good. Now it would be really cool if we could simulate this and see what's going to happen. So let's do that. I'm right-clicking on Setup 1. I'm going to say Simulate. There's all my tool paths. And I'm going to turn on the stock, and I'm going to turn off the tool paths.
So that green thing is the block of
If
metal
I
we
press
would start
play,
with.
we can see exactly what's about to happen. We clean off the top. We clean off the shelf.
And this is wonderful for looking for tool crashes or trying to reach down too far.
Now notice, it looks like it's leaving some material. That's okay. That's where the kidney bean shaped cutouts are going to come. So those will get actually cut away. And go down another cut. Again, you do not want to take off all the material at one time. Do nice gentle cuts, and that will give you a much better surface finish and it will be much more gentle on the cutting tool. Okay, you can see the edges come into view. We're on our last step down. There's our little kidney bean shaped cutouts. And all of that tall material is in the kidney bean shaped cutouts. So that's not a problem. That's all going to go away. There we go. We're cutting our bore. Now we start cutting out the kidney beans. Now if your part is really long and everything starts getting boring, you can come to the bottom and speed up the playback. I'm going to let it run for the sake of this video since you're seeing this for the first time. And each of the different operations has a different color in the progress bar. This is actually quite resource intensive, which is why you're seeing my video card flashing. And we just keep spiraling down. And that's it. Our milling operation is over. And we can check it out. That does look like our solid model. So now what we need to do is we're going to close out of this simulation. And we need to actually create the G-code. What I'm going to do is right click. Creating the G-code is called post-processing. I'm going to drag this window back over. So we need to give it information about what machine to write the code for. Right here, these are all kinds of different milling machines. The machine that we have is the Tormach. We've got to tell it where to send the code. In my case, I want to send it to the desktop. We always have to have a program number. So I'll make it 1002. And that's about it. And we just say post. I'm going to say put 1002 on the desktop. We'll hit save. And there is the actual code that I'm going to put on a flash drive and take over to the Tormach. You do sometimes have to manually edit this. You might want to change feed rates, something like that. But this is the code you're going to run. So you're going to go over to the Tormach. You're going to set the cutter right at the center origin, the program 000. And when you press play, it should do exactly what was in the simulation. Okay. Thank you for watching, and I hope this was informative.
Okay, so that is how you actually take a Solidworks solid model and actually make the thing, write the code for production. And again, Professor Coda is going to go really into detail with you guys on that. He may have you use the SolidWorks toolpath generator. I find it a little bit clunky, but you know, that's the usual thing of it's all in what you know and what you like. Okay. So back to the presentation and our little part here. So if we do actually need to mill square corners, we can do it. This is the common way you do it. You relieve the corners. So if I have some square object that's going to sit in this pocket, I just put these little holes at the corners to create space for the square part to install. Okay, this burns every new engineer. So do not get burned by square corners. I tell this to seniors, I tell it to grad students, and they still get burned by it. So if you need square corners, relieve them. Okay, if you absolutely do need square corners for whatever reason, there's another process called electric discharge machining, where we make a form tool to the exact shape, and then we electrify it and it sparks its way down into the part. Really slow, really expensive, really precise. It can be done, but you really need to justify that expense. Okay. And of course, if you're doing something with sheet metal where you're laser cutting or plasma cutting and you want to do square corners for that, no problem, have at it. A laser can make a square corner just fine. Okay, rigidity. Okay, this is one that a lot of people don't think of. So let's say that I'm trying to mill this really deep pocket with small radius edges. Okay, that tool is going to start to bend on you, and it might even break if you go too deep. So as a general rule, if I need to go down, say 3 inches in a part, I'll use a 1-inch end mill. I'll design my features around a 1-inch cutting tool. So a 3-to-1 aspect ratio of tool diameter to depth, that's pretty good. If I'm doing something really hard, like 4140 steel, you know, the stuff that you make gun barrels out of or aircraft frames, you know, I might go 2-to-1 on that. If I got something nice and soft that cuts readily, like 6061, okay, I might go down to 3.5-to-1, 4-to-1, something like that. But always use the largest tool that is reasonable, so it stays nice and stiff, doesn't chatter, and you get the geometry you want. Okay, so that whole discussion was all about having a tool that rotates and a workpiece that's stationary. The lathe is just the opposite. In a lathe, we typically make rotary parts, and we're going to turn the workpiece and the tool stays stationary. So typical operations are going to be facing, taper turning, doing the outside with fancy shapes. So this contour turning. You know, the lathe is quite a bit more sophisticated than just common milling. So I'm going to give it just this really high level discussion. Okay, we are not going to go into great depths on that one. Okay, and that's about it, guys. That's all I wanted to go over with you today. The rest of it is just talking about how to make a PDF. I think most of you have that covered. Is there anybody that's having trouble with PDFs for the final project?
Can you just run through that real quick, like the basic, just what you need to do?
Sure, Logan. So this was based on previous years when we could all be together. So create your individual PDFs in SolidWorks. And all you're going to do is do File, Save As, and choose PDF with the drawing up. That'll create the individual PDFs. Then normally what I have the students do is you come over to Crosby Hall. You can open up the full boat of Adobe Acrobat Writer, and you'll go from your flash drive, and you can literally just drag it from your flash drive right here into the file organizing window. Once you drag the files in, you put them right here. Now you can drag and drop them. You can reorder them however you like. When you submit your final package, I want to see the top level model first. Then I want to see all the sub-assemblies. Then I want to see all the piece parts. Okay. So it's just like having a discussion with a vendor. You want to show them the big idea first, then you go down into the details. Same idea. Okay. You guys are welcome to use the Crosby PC if you can get there. You know, you guys may be who knows where in the world at this point, but if you can get there, you're welcome to it. And last item, so I sent out an email yesterday on 12/9. We're going to run our engines. We will do it virtually this year. Most years I have you guys all come pile into Crosby and we ran them on the welding table. Okay, can't do that. But if you get your engine running, snap a nice little piece of video. We'll pass the screen around and hopefully we get a bunch of them running. Typically in any given year, we get like 10 to 15 of them running. So if we could do that this year, that'd be great. Any other questions, folks, before we call it a day?
I was just wondering if you had a chance to look at my draft of my Sterling engine that I sent you.
I have not, honestly. I was trying to get all of the exams back over the weekend. The exams themselves are going quite well. The class average right now is, I want to say it's like 80 or 85. It's up in the B range, which is higher than I typically target, but okay. You know, if you guys did it right, so be it. I'm happy with that. So it's not bad like the modeling test, and I certainly don't foresee any retest on this one, which, you know, we would struggle to even get it in time-wise.
So then we probably won't end up having a final as well, right?
Well, again, I'm going to leave that up to you guys. I will say that this exam saved a bunch of you from a bad first exam. So, I mean, I'll send out an email. If anybody feels like, oh my God, I just need a test, I'm just dying to have an exam, send me an email. But honestly, this second test went pretty much the way it always does. A lot of people were like within 5 points of their first exam. There are a couple people that really went up, but on average, it was pretty close. And I tend to see that when I do give a final, it's pretty darn close. It doesn't change the grades all that much. But again, I'm going to leave it up to you guys. If you want me to write one, I will. I mean, you paid for the course. You should get your full measure if you want it. Anything else to talk about, folks?
I sent my Sterling engine like final package just to your email. Should I send it to the grader one?
I already forwarded Ethan.
Okay.
That's all good.
Thanks.
Yeah. Okay, then we are done here. Have a great day. Hope your power comes back. And stay safe, folks. Talk to you later. Bye.